Okay. So this is very important. So that's why I'm stressing it so much. Okay. So I have about 10 minutes left, and I can see that everyone is here today. So I don't have to take attendance. Okay. So most quantum systems are in an eigenstate of the S squared operator. This is another way of saying that most quantum systems have some well-defined spin eigenvalue. Okay, so suppose we have such a quantum system with such a quantum state, and its state is psi. Then we can express it. So it has some given S value. So we can now express this as in terms of the eigenstates. Okay, so I'm just using the decomposition of an identity because for a given S, my identity operator on the spin degrees of freedom is just sum over m from minus s to plus s of sm. These are just the projection operators, right? Okay. So now we can write this as sum over m goes from minus s to plus s. What is this? This is the wave function Sm. This is going to be some matrix. Okay. Now suppose that we choose suppose we want to now rotate this system. So we want to change the orientation of the spin. So if we want to change the orientation of the spin of the system, then we need to apply to psi the following operator. U, suppose we want to change it by some theta, some angle theta around some axis n. And this is going to be e to the power minus I theta n dot s. Okay. This is an analogy with what we saw for the orbital angular momentum and also the translation operator. Now let's choose our coordinate system. Let's choose our coordinate system in such a way that n dot s is s of z. Okay, so now if I rotate my system by 2 pi, then what is going to happen? It's going to this unitary operator is going to be e to the power minus 2 pi I s of z acting on the basis vectors which are s of m. But of course, m is going to be the eigenvalue, just as we saw in the orbital angular momentum. It's going to be 2 pi I m s of m. But here there is no constraint that this thing has to be 1. So m can be integer. If m is an integer, then we see that under rotation, these factors are 1. Under rotation, our system will remain unchanged. And such systems are called, particles are called bosons, okay? On the other hand, so bosons have, integer s. Because if m is integer, s is going to be integer. The spin is integer. But m is half integer, then we see that, this is going to be -1 if it's m is half integer, because if it's at 3 halves, then this 2 will cancel with the half, and we'll be left with an odd number. And an odd number of, rotation by pi is going to give me a -1. So if m is a half integer, then psi will, if you do a rotation under rotation by 2 pi. So under rotation by 2 pi, psi will go to minus of psi. And such particles are called fermions. Okay, fermions have half integer spins. So this is kind of a weird thing, because in real life, you assume that if you take a phone and just rotate it around some axis by 2 pi, it comes back to its original self. But in the quantum world, fermions are objects such that if you rotate them by a complete 2 pi angle, they pick up a minus sign. Okay. So this is the root of the Fermi-Dirac statistics. And so people find it counterintuitive and say, oh, this shows that this is quantum, blah, blah. But even in classical worlds, there are systems in which rotation of the system, part of the system by 2 pi, does not lead you back to the original state. You have to rotate it twice. And do you know about this rotation? This trick. If not, I will post a video on the Slack channel made by one of my former students and a friend, where he shows the application of this weird rotation that does not bring you back to the same configuration. He uses that in the context of martial arts as a karate chop in karate. Okay.
Wow, that's impressive.
Yeah. Felix is a cool guy. He's a friend and a former student, and he was at Oxford, and I actually went to visit him a few years ago. And he's now a faculty at Cardiff. Okay, so so basically you can do that by, say, if you take a cup in your hand, and if you rotate the cup without moving, and you rotate the cup by 360 degrees, then you will see that your hand is in a twisted position. But if you rotate the cup by 720 degrees, then your hand will be in an untwisted position again. Okay, so I will post some. So I think that this is all we have time for today. So any last questions? I will post lecture 5 tonight and lecture 6 maybe tomorrow. Okay. Okay, any other questions? So I'm very happy that you guys asked questions today, even people who usually don't speak. So please keep that up, okay? This really, really makes a difference. There are no, all questions are good. Sometimes I will ask you to do stuff by yourself, because I think if you apply yourself, you'll be able to do that. But please keep asking questions, okay?
Yeah, asking questions has been a lot of help for me these days.
Okay, very good. Yeah, don't be shy. Okay, anything else?
No, sir.
Okay, if not, then let's, okay, you guys continue with the tutorial on Saturday, okay?
Okay, sir.
Okay.
The later two questions.
Yeah, because I think it's a very useful tutorial because you get a overview of the position representation and
Yeah,
you learn a bunch of new stuff.
yeah, I'm struggling a lot with the tutorials, so it's really helpful. Not gonna lie.
No, it's good. Yeah.
Yeah,
Okay.
struggling is good for me.
Well, yeah, struggling means you are learning.
Yeah.
So these are stuff from distribution theory, functional analysis. But you don't need to know all of that. You just need to know, okay, oh, this is cool that you can actually think of, infinite dimensional operators in terms of delta functions or, derivatives acting on delta function, and so because you don't kind of think of the differential operators, the derivative as matrices, right? But there's a way of thinking about them in terms of matrices, and that's what I show in the tutorial. And then you also have to, and also the distinction between what is Hermitian and what is self-adjoint is also clear in the tutorial. You will see.